Space, the final frontier. These words ignite our imaginations, hinting at endless possibilities beyond our world. But have you ever stopped to consider the wonders of flight right here on Earth? Helicopters, those marvels of engineering, possess a unique grace, their spinning blades carving through the air with breathtaking agility. Yet, this dance of lift and thrust comes at a cost, one often heard as a distinctive thump-thump-thump echoing through the sky. This sound, my friends, is a telltale sign of a fascinating phenomenon known as Blade Vortex Interaction, or BVI for short. Imagine a helicopter blade slicing through the air. As it spins, it leaves behind a swirling trail of air, much like the wake of a boat. These swirling trails are called vortices. Now picture another blade following closely behind, encountering these invisible whirlpools. This encounter, this clash of blade and vortex, is what we call Blade Vortex Interaction. It's a complex dance of aerodynamics, a delicate interplay of forces that can have a significant impact on a helicopter's performance, noise, and even its structural integrity. To truly grasp the intricacies of blade vortex interaction, we must first journey into the realm of fluid dynamics, a world where air itself behaves like a fluid, flowing and swirling in response to forces around it. As a helicopter blade cuts through this invisible ocean of air, it generates lift, the force that allows the helicopter to defy gravity and soar through the sky. However, this lift doesn't come without a price. Along the edges of the spinning blade, a pressure difference is created, forcing the air to curl and spiral, forming the aforementioned vortices. These vortices, like miniature tornadoes, trail behind the blade, carrying energy and influencing the flow of air around the helicopter. Now, when a following blade encounters these vortices, a fascinating interaction occurs. The swirling air of the vortex can either push or pull on the blade, altering the pressure distribution across its surface. This sudden change in pressure creates noise, vibration, and can even affect the helicopter's lift and handling. Blade vortex interaction is not a one-size-fits-all phenomenon. It manifests in different forms, each with its own unique characteristics and implications for helicopter design and operation. Think of it as a symphony of interactions, each type playing a distinct role in the overall performance of these aerial marvels. Parallel BVI. Imagine two blades passing in close proximity, their vortices aligned parallel to each other. This is parallel BVI, a scenario often encountered during low-speed flight or hovering, where the vortices from preceding blades linger in the rotor disc, influencing the blades that follow. Perpendicular BVI. In contrast to the aligned vortices of parallel BVI, perpendicular BVI involves a blade slicing through a vortex that's perpendicular to its path. This type of interaction is common during maneuvers like descent or turning, where the helicopter's blades encounter vortices from different parts of the rotor system. Oblique BVI. As the name suggests, oblique BVI occurs when a blade encounters a vortex at an oblique angle, neither parallel nor perpendicular. This type of interaction is often a combination of the two, with the blade experiencing both lifting and pushing forces from the vortex. Orthogonal BVI. The most severe form of BVI, orthogonal BVI, happens when a blade encounters a vortex at a perfect 90-degree angle. This head-on collision creates the most significant pressure fluctuations on the blade, leading to increased noise, vibration, and potential structural stress. Section 4. The Noise Whisperers. Why BVI Matters. Why, you might ask, is this invisible dance of blades and vortices so important? Why do engineers and scientists spend countless hours studying this phenomenon? The answer, my friends, lies in the quest for quieter, more efficient, and safer helicopters. You see, blade vortex interaction is a major contributor to helicopter noise, that distinctive thump-thump-thump that can be heard for miles. This noise is not only a nuisance for those on the ground but also a limiting factor in helicopter operations, especially in urban environments. Furthermore, BVI can induce vibrations that can affect the helicopter's stability and handling, making it more challenging for pilots to control. In extreme cases, these vibrations can even lead to structural damage, compromising the safety of the aircraft and its occupants. Understanding and mitigating BVI is therefore crucial for improving the overall performance and safety of helicopters. By unraveling the secrets of this complex phenomenon, we can pave the way for quieter, more efficient, and more robust rotorcraft. Section 5. Unraveling the mysteries of BVI prediction methods. Predicting blade vortex interaction is like forecasting the weather, requiring sophisticated tools and deep understanding. Scientists use wind tunnels, analytical methods, and CFD to study BVI. Wind tunnel tests provide controlled environments for BVI study. Analytical methods use mathematical models for cost-effective predictions. CFD simulations offer detailed BVI analysis but need significant resources. Hybrid methods integrate all approaches for comprehensive understanding. Section 6. Quieter skies, safer flights. Benefits of BVI Research. The pursuit of understanding and mitigating blade vortex interaction is not merely an academic exercise. It's driven by a desire to make helicopters quieter, more efficient, and safer for everyone. By unraveling the mysteries of BVI, we can unlock a future where these versatile aircraft play an even greater role in our lives. Imagine a world where helicopters can operate silently over bustling cities, providing emergency medical services, transportation, and aerial surveillance without disturbing the peace below. By reducing BVI-induced noise, we can make this vision a reality, opening up new possibilities for helicopter use in urban environments. Moreover, mitigating BVI can lead to significant improvements in helicopter efficiency. By reducing the drag and vibrations caused by blade vortex interactions, we can enhance fuel economy and extend the range of these aircraft, making them more environmentally friendly and cost-effective to operate. But perhaps the most important benefit of BVI research lies in the realm of safety. By predicting and mitigating the vibrations and structural stresses caused by BVI, we can design more robust helicopters that can withstand the rigors of demanding missions, ensuring the safety of pilots, passengers, and those on the ground. Section 7. The future of rotorcraft advancements in BVI research. As we venture further into the 21st century, the quest to understand and control blade vortex interaction continues to drive innovation in the field of rotorcraft design. Researchers around the world are exploring novel concepts and technologies that promise to revolutionize the way we think about helicopters. One promising avenue of research focuses on active rotor control, where onboard computers and sensors constantly adjust the pitch and angle of the blades to minimize BVI. Imagine a helicopter that can anticipate and counteract the formation of vortices, effectively smoothing out its ride and reducing noise. Another area of exploration involves the use of advanced materials and blade designs that can alter the way air flows around the rotor system, reducing the strength and impact of vortices. From bio-inspired blade designs that mimic the wings of birds to shape-changing materials that can adapt to different flight conditions, the possibilities are endless. The future of rotorcraft is bright, and blade vortex interaction research will undoubtedly play a pivotal role in shaping this exciting frontier. As we continue to push the boundaries of our understanding, we can look forward to a future where helicopters are not only quieter and more efficient, but also safer and more versatile than ever before.